In this lesson, we're going to talk about network topologies. And when we talk about topologies for networks, we're going to be talking about it in one of two ways. First, we can talk about it physically. How are these devices physically cabled and connected together using various types of media? And the second is how it is done logically. When we talk about it logically, we're talking about how the traffic is actually going to flow in that network. So here on the screen, you can see I have a logical diagram of what a network looks like. You can see where the workstations are, the routers, the switches, all of that stuff. But this is not how the network actually looks in the real world. For example, that Windows 7 machine in the upper left might be on the third floor of the building, while the Windows 2012 machine on the upper right may be all the way down in our basement. You really don't know, based on this diagram, where these things are physically because this is a logical topology. I'm just concerned with the way the data flows, not the way it's actually cabled. Now, here we're going to learn how to read these diagrams throughout the rest of this course and what each of these icons mean, but right now, that's not important. I just want you to realize that there's a difference between a logical and a physical topology, and that difference is one is focused on the logical or network flow, and the other is focused on the physical layout of the cabling. So, what are some of these options that we have for different topologies? Well, the first one we have is what's known as a bus topology. This is where you use a single cable that runs the length of the entire area that needs network connectivity. Each machine that's a laptop or a desktop or a server would then tap into that cable using either a T-connector or a vampire tap. Now, you may be wondering, what's a vampire tap? Well, it was an old way of connecting networks. Essentially, we would take a big, thick metal cable and run it down the room where all the computers would be connected. And then each computer would have a clamp that would bite into the cable, and it would actually make the connection to the network that way. And that's why we called it a vampire tap. Now, this is a very old technology. It was used back in the 80s and 90s. We don't use this today. But we still do have some bus topologies out there. We don't use them very often, but they do still exist. If you see a bus topology, all the devices on this cable would form what's known as a single collision domain. This means, as you can see here, there are 6 different devices here trying to talk. If they all try to talk at the same time, you would just have a collision because they're all sharing the same cable. So they'd have to instead take turns. The next topology we're going to discuss is known as a ring topology. And this uses a single cable like a bus does, but instead of it being in a straight line, it's going to run in a complete circle. Each device in the ring can then talk on that cable, but again, they have to wait their turn or you're going to have a collision. Data would travel around this in a single way, either clockwise or counterclockwise, depending on the configuration of your network. Now, when we had these, because of that collision we wanted to overcome, what we did was we had what's called a token ring. And a token was just an electronic tag, essentially, that was passed around logically from computer to computer as they were going to talk. This would allow them to take turns. So if you think back to when you're in elementary school and everyone's sitting around a circle and there's 20 kids and one teacher, the teacher may have had the talking stick, and they gave the stick to a child, and that child can then talk. Then they would take that stick away and give it to a different child, and then that child could talk. And this way, everyone could hear what everybody else was saying, without any collisions or anyone talking over each other. That's the idea of a token ring network. This eliminates those collisions that you had back on the bus network. Now, when you had these rings, they still were vulnerable to being broken. If you cut the cable, that would take down the network, so there was no redundancy. Now, there is something known as a FIDI ring, which is a fiber distribution network. A FIDI ring actually uses 2 rings, one on top of the other. One operates in a clockwise direction and the other operates in a counterclockwise direction. When you use a FIDI ring, you do get redundancy because if one of those rings is broken, the other one would take over the network load. Now, for the Network Plus exam, if you see the word ring, I want you to think about a FIDI ring, those fiber optic distribution rings, because these days, that's the only type of ring topology we really use in our networks. For the exam, anytime they ask you a question and ring is an option, I want you to think ring equals redundancy. Now, in the real world, if you had a standard token ring with a single ring, there's no redundancy there. But for the exam, I'm telling you, they're talking about FIDI rings. So when you see ring, think about redundancy. You might get a question that says, which of these topologies is redundant? And they're going to give you options like star and bus and ring, and the answer is going to be ring. All right, I think I stressed that and repeated that enough. You're going to remember ring equals redundancy for the exam now, right? All right, let's move on to the next topology. The next one we have is called a star topology. You'll notice here all of the outlying machines are talking to this central point. This central point is normally going to be something like a switch. Now, this switch is where all of the things are going to connect back to, and this happens in most of our networks these days. You can use it with fiber or copper or even wireless if you wanted to, and this is going to be using a star topology. We call it a star because everything is bursting out like a star pattern. But the problem with this is that you have this one central device. And so if I have a switch here in the middle and the switch fails because it loses power or we cut the cable or something like that, the entire network is going to fail because it's a single point of failure. So remember with a star that you always have this single point of failure. Even though these are very, very common to use and very inexpensive to use, we do have this single point of failure sitting right there in the middle. Now, the next topology we have tries to overcome that, and it's called a hub and spoke. Now, a hub and spoke topology is used for connecting multiple sites together. The reason we call it a hub and spoke is if you think about it the way the airlines operate, it looks like a hub and spoke. These usually have hubs, like for instance where I live in Baltimore, there's a hub for Southwest Airlines. And if I wanted to go to Connecticut and go to California, you'd actually fly from Connecticut to Baltimore, which is the hub, and then go out over to California. This allows them to centralize their operations into hub cities. There's usually each airline has 2 or 3 or 4 hubs, and all the flights go through those. So because you go to the hub first and then you go out to the spoke cities. This is the same concept with the network. It's very similar to the star, but there's multiple WAN links and multiple places that these hubs can exist. So it's almost like a hybrid of taking those stars and connecting them together. So as you can see here on the screen, I have Denver and Los Angeles as the hubs in my network, and everyone else is going to be a spoke. So if I wanted to go from Atlanta to Seattle, I have to go from Atlanta to Denver and Denver to Seattle. Now, if I wanted to go from Minneapolis to San Francisco, I could go from Minneapolis to Denver and Denver to LA and LA to San Francisco. No matter which way I go, I have to go through either LA or Denver because those are the hub nodes. It's not redundant fully because if one of those central offices like Denver or LA fails, we're going to lose large portions of our network. But it is better than a single star. Now, because of this, losing half of our network is a bad thing, right? This is a problem. And if we're looking for full redundancy, we would want to go to what's called a full mesh topology. Now, full mesh is awesome when you talk about redundancy. Every single node or device is connected to every other node or device. This works really, really well if you have a small network, 2 or 3 machines. But as I start increasing the number of machines, it gets to get pretty crazy pretty quickly. Optimal routing is always available when you're dealing with full mesh because every machine can go direct with one jump over to the machine they want to get to. So in this example you see, I have 6 machines on the network. Now every single one of them is tied to each other. So if I was doing this physically, I would need to have 5 network cards for each of these machines and 5 cables going from each of those machines. That's a lot of technology that I have to add to be able to connect these machines together, right? And so if I counted up the number of black lines there, how many different connections are there? How many lines would I actually have to run? Well, there's going to be 6 machines times 5 cables each, which is 30, divided by 2, which is 15. So there's actually going to be, for 6 machines, it's going to take me 15 cables. Now, if I go to 7 machines or 10 machines, it gets pretty crazy and gets really expensive really quickly. And this is why you're never really going to see a full mesh in a physical network. Instead, you're usually going to see full mesh more as a logical method. If you have something like nuclear command and control, they may want to have full mesh and they'll go through the expense because they have a zero defect mentality there. But in your office and business networks, you're not going to be seeing full mesh. It's just too expensive and too complicated. Now, what might you see in your business networks? Well, you might see a partial mesh network. Now, a partial mesh network is a hybrid of the full mesh and a hub and spoke. Using this design, we can provide optimal routing between some sites, but not all of the sites. And so to get this right, you have to do a good survey and figure out where the busiest sites are and where the slow sites are. So as you can see here on the diagram, if you start drawing your finger around, you can get to everywhere else, at least going through 1 or 2 different ways. Sometimes you're going to have to go through one of those central sites, and if one of those central sites goes down, you can still get to everywhere else because we have the right partial mesh set up. So this partial mesh works really well and gives you that additional redundancy you're seeking. Now, to get it right though, you do have to understand your traffic patterns and know where to put those main hubs, and it basically then becomes a modified hub and spoke where we have more hubs than we did before, and this allows us to have a better redundancy than a single hub and spoke configuration.